Welcome back to our next lesson, where we'll start to look at rates of reaction and the idea of collision theory. Okay, so have a think about what we did last time. We did discuss a few different terms. Do you recall any of those terms that we had? And we did that pre-test, don't forget. Make sure you've done that one. These are the terms we looked at last time. Take a moment to pause the video, cast your eye down that list and see if there's any that come back to mind or you recall from previously. And if you'd like the answers, we can find them there. Once again, just pause, look down that list, make sure you understand those terms. Okay, so what are we doing today? What we're going to do is we're going to understand how collision theory works and how it can explain the reaction rate. And we're going to look at the four factors that affect the rate of reaction. Those four terms there is your main takeaway from this particular lesson. Know those. So some reactions proceed really, really quickly. So usually combustion reactions, such as methane burning, is very, very rapid. Whereas rusting of iron, which is an example I gave last lesson, tends to be quite a bit slower. So the speed that this reaction actually happens is determined by the reactants that we actually start with. Okay? And there's other factors about how those reactants are put together to make the reaction occur. So the four things we had at the start there is these ones here: temperature, concentration, surface area, and catalysts. What's the temperature of the reactants? How concentrated are they? How much area is there to physically come into contact to react? And can we add something like a catalyst to speed up the reaction? And these are important because the molecules have got to collide. And that's the idea of collision theory that I mentioned a second ago. For the reactants to actually react, they have to physically come together with each other or to collide to form the products at the end of the reaction. So we're going to have a look at another PowerPoint that I've got following this in just a minute. It'll go through those four factors in detail. All right. However, we do have a question we're going to ask. What I've got a picture of here is basically hydrogen peroxide. And you can see it just looks a bit like water sitting in a beaker there. But hydrogen peroxide is basically H2O2. So it's kind of like water, but it's got extra oxygen atom in there. Tends to be a bit nasty. If it gets on your hair or things like that, it will bleach your hair white. But it tends to break down, and kind of a bit like when you pour a soft drink, you start to see little bubbles appear on the outside, like forming on the container like that. Peroxide does the same sort of thing. And if you've got some in the home, I suggest you go and grab some, pour it into a little clear glass and leave it there for a little bit and see how long it takes for the peroxide to break down, and you start to see the little bubbles forming on the side there. All right, you'll see it break down and little oxygen bubbles and things like that appear on the side of the glass container. But I've also got another reaction to compare it to. This one here. Grab that link, go and watch it. It's from the Big Bang Theory. It's the story about how the elevator in their building stopped working, and it has a different reaction. And what I want you to do is have a think about those two reactions. Think about the elevator reaction, think about the peroxide reaction, and just see if you can sort of put in words what's the difference between those two reactions. Okay, so let's go on to this next activity. Rates of reaction. And they're the four things we're going to run through. So the particles are going to collide. That's what's causing the reaction. The temperature, the concentration, the surface area will all, and catalysts will all play a role in how quickly that reaction occurs. Notice on concentration, I've got concentration and pressure, because concentration more refers to solids and liquids. The pressure refers to gases. If you put it under a lot of pressure, it's going to concentrate the gas molecules more. So here we've got some examples of some reactions. Rusting is obviously a good example of a very slow reaction. Baking cookies or a cake or something like that, or frying an egg, that type of thing, tends to be a quick reaction. You're adding the heat to it to drive that reaction forward. Or explosions, well, that's even quicker again. Something like the fireworks there or a bomb going off are very, very, very quick reaction, and usually a lot of energy is released in a very short period of time. So when we think about why reactions are faster than others, it's about how quickly the reactants physically can collide with each other, and that's the collision theory. So if we look at our picture on the screen there, you've got the red reactants, little red guys, and then the blue ones, and they physically have to collide with each other for a reaction to actually occur. That's the idea of collision theory. So, temperature, concentration, surface area, and catalyst are our main factors that will keep this, that will affect how quickly our reaction actually occurs. And I keep talking about this because, as we mentioned last time, chemists want to control how quickly a reaction goes. If you're making a product that you're trying to make in a factory to sell that product, you want a very efficient, quick reaction to make as much of it as you can to sell more of it. If you consider the example like a metal boat, you want to slow down that rusting reaction so your boat doesn't rust away. That's why we want to control our reactions. Okay, so which of the following will increase the rate of the following reaction? So this is a burning reaction here, wood plus oxygen. So that's effectively just a hydrocarbon is the wood, carbon and hydrogen, combines with oxygen from the air. You end up with a little bit of water vapor and a stack of carbon dioxide. All right. Now the reaction generally doesn't burn completely, and the wood has other things in there that are not going to burn completely, and hence you get the ash and so on left behind, but which is essentially a bit of carbon. But you get a lot of carbon dioxide come off as well. So how are we going to increase the rate of reaction? First one here, if we fan the flames of the fire. If we fan it, what we're actually doing is getting more oxygen into that reaction. So that's going to increase our rate of reaction. If we chop the wood into smaller fragments before we light it, the air can physically get around it because you've increased the surface area and the reaction will go quicker. If you've ever had a campfire or ever had a wood heater in the colder months, chopping the wood into smaller and smaller bits means it will burn faster. You get a lot of heat released, but your wood burns up quicker. In the third one here, packing the timber so that there are no spaces between segments of firewood, well, you're going to stop the oxygen getting to the wood, and hence you're going to slow it down. So number one will speed up our reaction. Number two will speed up our reaction, but number three won't. It will slow it down. All right, so let's keep going. Let's have a closer look at some of these factors. How does the temperature affect the rate of reaction? On the left-hand side there, think of like a cold morning where you're sort of feeling a bit sluggish and you don't really want to get out of bed, versus the right-hand side there where it's a warm day and you can get up and you can get active and so on. And that's kind of a model for how reactions occur. The hotter they are, like on the right-hand side there, the faster the particles will vibrate and move around, hence the faster they'll collide with each other and the faster the reaction occurs. So higher temperature, faster the rate of reaction. So in a lot of reactions, 10 degrees increase in temperature will approximately double how quickly your reaction goes. So how does this work? At a higher temperature, this is our explanation here. The particles have more energy, which means they move faster and they will collide with each other quicker. All right. As they collide, they have more energy because they're physically moving faster, and so the number of collisions increases, and the actual reaction, where the particles are combining in some way, will happen easier. So let's look at an example. When propane gas, like barbecue gas, reacts with oxygen ignition flame, a spark is required to get the reaction to begin. In terms of collision theory, explain why this is necessary. When the propane gas, like your barbecue gas, reacts with oxygen, it generally needs a little bit of energy to get it started. So your spark is that little bit of energy. So the spark provides energy to start the reaction. There's an abbreviation for energy and reaction. Okay, so the next question, why does the reaction continue without requiring a continuous spark? It's because the reaction releases energy, and as it releases energy, this helps the next molecule next to it have enough energy to ignite with the oxygen and so on. So the reaction releases energy to keep itself going. And allow all the particles to react. Okay, let's look at concentration and pressure. So the higher concentration of the dissolved reactant, the faster the reaction will go. So why does this actually work? If you look at your diagram on the left here, there's a lower concentration, and just think of the probability of those particles that are moving around in random directions, random whatevers. What's the chances they're going to hit each other and physically collide for the reaction to occur? And compare that to the one on the right here. Obviously the one on the right, there's more particles because they're more concentrated, hence they're going to hit each other more. Think of your concentration just like your cordial. Low concentration is a weak cordial, high concentration is where you add more cordial to it and it's stronger. That's like this example here. And in our particle model of reactions, the physical particles have to physically collide with each other, so the more of them, the more they're going to collide, the more the reaction is going to occur. And with gases, we generally don't talk about gases in terms of concentration, we talk about it in terms of pressure, and that's the same story. Alright, let's have a look at surface area and catalysts. So if we look at the example here, surface area there is low because it's just one big block, but as we start to cut it up, we are increasing the surface area, and the further we cut it up into smaller and smaller bits, there's more physical sides for another reactant to react with to actually collide and drive the reaction forward. So this is sort of an example of breaking a large object up into smaller and smaller bits until the higher surface area you end up with a very, very fine powder, hence more physical surfaces for the reactants to contact together, the more the reaction is going to go forward. What I didn't mention in that slide was the idea of a catalyst. A catalyst is basically a reactant that you add into a reaction. It makes the reaction go quicker, but it's not generally used in the reaction. Okay, we use catalysts in all sorts of reactions, chemical reactions. If you think of a catalytic converter in a car, basically cleans up your exhaust in your unleaded cars. It's a section in your exhaust pipe that effectively makes the exhaust gases react, so they're a little bit just marginally more safer for the environment. Alright, so let's start to sum up. Have a look, just pause the slide here, see if you can answer those questions before we go through the answers. So the higher temperature, the higher the rate of reaction. At a higher temperature, the particles have a higher energy. This means that they move faster. Sorry, my writing's a bit messy. And are more likely to successfully collide with other particles. The concentration of a dissolved reactant, the faster the rate of the reaction, the higher the concentration, the faster the reaction. Okay, have a think about what we've done today. Thanks for coming, and I'll see you next lesson.